Hello, welcome to another video on how to solve ODEs in MATLAB. In this video, we want to look at how we can solve a simple ordinary differential equation. So where you have the fusion of a compound A through a long tube. So the tube is 4 centimeters long, and as the compound A diffuses, it gets consumed by reaction. So at the beginning, the initial concentration was 0.1 molar concentration, and then at the end, the concentration is consumed quickly. So it means at the end of the tube, it becomes zero. Okay, so you have this the diffusion coefficient and the reaction rate constant. So we want to see how the concentration changes along the length of the tube. So how do we do this in MATLAB? Okay, so first we need to define the parameters that we have. We have D, the diffusion coefficient, K, the reaction rate constant, and then the length of the tube, L equals 4 centimeters. Then you will need to write the function. So as an anonymous function, as you know, f equals at x comma y. So because you're doing it with respect to x, so the derivative is with respect to x. So x comma y, and then the y in, as you know, uh, is going to be like a matrix of some vectors. So what we want to solve basically is this equation, d squared a dx squared minus ka equals 0. So you need to first rewrite the equation so that you have only d squared a dx squared on the um, left-hand side. So d squared a dx squared will be equal to ka over d. So this is what you're trying to solve. Now, but in MATLAB, even Python, GPROMs, all these programming languages, they don't solve second order differential equations directly. So you need to first convert them to a system of ordinary differential equations. So what you need to do first is to define a new variable for A, so which is a differential variable here. So here we say that if A equals y1, for example. So if A is y1, it means when I differentiate A with respect to x, so I can call that y2. Okay, so y1 and y2. So those are the variables that then I'm going to use. Um, and which means that d square a dx squared is basically k over d. Then a, instead of writing a, I can write it as y1 because a is y1. Can replace this a with y1. Okay, so and that is what I have in this equation. So I wanted to return the y2 is I wanted to return the differential. It's going to return both the first order and the second order differential. So the first order, this is dA dx is y2, so which is returned here, and then the second order is returned there, which is the right hand side here. So k over d multiplied by y1, which is that. Okay, so that's what is going on there. So the function returns a vector of the first order and the second order derivatives. Then the boundary conditions similar, it takes, you have YA and YB, which is basically a way of defining the boundary at the inlet and the exit. So in the inlet at when in nx is 0, and the exit when x is equal to the full length of the tube. So the boundary conditions, the way MATLAB will accept it is to write everything equal to 0. So that's the way it's going to accept it. So the boundary conditions that we have, we'll have to write it in that form. So, why we have y1. So here you say y1 equals to mine is equal to 0.1. So because a is equal to 0.1 in the problem. So if you rearrange that, so we have y1 minus 0.1 equal to 0, and that is what we have here with our under condition. Then yb1, which is at the exit, that is equal to 0. So at the exit, yb 1 is equal to 0. That's what that means. YB, which is why y1 is equal to 0. But B indicates at the x equal to L. So that's how you create the boundary condition. Then the initial guess, you create the initial guess by using this BVP in it. So boundary value problem in it. The link space specify the starting point, the finish point, and the number of steps, the number of points or number of grid points that you have, and then for and then you specify what you have at x at the beginning, at a equal to 0, and then at a equal to for the second variable. So you solve BV. You can use this function BVP for C. This is one solver that you can use. You pass the function, you pass the boundary condition and the initial condition, and then you plot the result. So x and a. So x, if you plot x is link space 0L. So basically, you are creating another array. So from 0 to L, increasing the number of grid points, and then we want 100 grid points, and a, a is basically extract the solution at those grid points, and then you plot them. So that's basically what you're doing here. So you plot x and a. So you grab all for a, you grab the first row and all columns, and then you plot it. Okay. So when you plot it, when you run it, what do you get? If you run that code, so you should generate the profile of the concentration from 0, a equals 0.1. So this is when x is equal to 0 and when x is equal to 4. So the concentration drops to 0. Okay. So that's it for this video, and I will see you in the next. Bye-bye.